It shrinks into a dot against the vast blue canvas of the sky, disappearing forever. Most of us see this as a harmless, whimsical moment. We don't think about what's inside or where it came from. We just see a lost toy. But here's the surprising thing. We should. That little balloon is carrying a precious and finite piece of our planet into the void. The same invisible gas that lifts that simple toy is a critical component in some of our most advanced and life-saving technologies. Our most sophisticated hospitals depend on a steady supply of helium to operate their MRI machines, which are essential for diagnosing everything from brain tumors to torn ligaments. The powerful rockets that launch satellites into orbit and carry astronauts to explore space rely on helium to keep their complex fuel systems running safely and efficiently. The entire infrastructure of modern medicine and scientific exploration is surprisingly dependent on this one, seemingly simple gas. So the next time you see a balloon drift away, think of it a little differently. It's not just a lost toy. It's a tiny, visible symbol of a much larger, invisible problem. We are using up our planet's limited supply of helium at an alarming rate, and much of it is for trivial purposes. The consequences of a world without enough helium aren't about quieter birthday parties. They are about compromised medical care, stalled scientific research, and a very real bottleneck on our technological progress. The silent ascent of that balloon is a quiet warning, telling us we need to pay attention to what we are so carelessly letting slip through our fingers. The story of helium doesn't start here on Earth. It begins 93 million miles away with our very own star. Back in 1868, during a total solar eclipse, Pierre Janssen pointed a spectroscope at the sun's corona. He was trying to study the fiery atmosphere of the sun, and he saw something no one had ever seen before. In the spectrum of light, among the familiar lines of color that represented known elements, hydrogen, sodium, there was a strange, bright yellow line that didn't match anything. It was a complete mystery, a chemical fingerprint without a name. At first, many scientists were skeptical. They thought it might be a mistake or perhaps an element that only existed under the sun's extreme conditions. Norman Lockyer, an English astronomer, was convinced it was a new element unknown on Earth. He proposed naming it helium after the Greek word for the sun, Helios. For over 2 decades, helium was a celestial enigma, known in the heart of the solar system, but never found on Earth. It wasn't until 1895, nearly 30 years later, that helium was finally identified on Earth. Scottish chemist Sir William Ramsay was conducting an experiment with a mineral called cleavite. When he treated the rock with acid, it released a gas. Ramsay collected the gas and analyzed its spectrum. To his astonishment, he saw the exact same bright yellow line Janssen had spotted in the sun's corona. The alien element from the sun was here all along, trapped inside rocks under our feet. A shocking, profound discovery connecting our world to the cosmos. A monumental moment for science. Finding helium on Earth was like finding a piece of a distant star in your own backyard. It confirmed that the elements making up our planet are the same as those building the rest of the universe. People had seen helium's signature in the sky long before they held it in a lab. This unusual origin story, from celestial mystery to earthly reality, is just the first chapter in helium's strange and fascinating life, setting the stage for its indispensable role in our modern world. So, what makes helium so special? Well, for starters, it has some of the most extreme properties of any element on the periodic table. It's the second lightest element, second only to hydrogen. This is why it floats. A balloon filled with helium weighs less than the same volume of air, so the denser air pushes it upward just like a log floats in water. But unlike hydrogen, which is famously flammable, think of the Hindenburg disaster, Helium is what chemists call an inert gas. It won't burn, it won't explode, it won't corrode the pipes it flows through, making it incredibly stable and safe. But its most extraordinary property reveals itself when it gets cold. Really, really cold. Helium has the lowest boiling point of any element, turning into a liquid at minus 269 degrees Celsius, minus 452 degrees Fahrenheit. That's just 4 degrees above absolute zero. At this temperature, nearly everything else is frozen solid. But liquid helium is where things get truly bizarre. It becomes a superfluid, a state of matter with zero viscosity. This means it can flow without any friction, seeping through microscopic cracks and even climbing up and over the sides of its container in defiance of gravity. This unique ability to stay liquid at unbelievably cold temperatures is helium's superpower. It is the ultimate refrigerant, the key to unlocking the world of cryogenics. There is simply no other substance that can get things as cold as liquid helium can, and stay liquid while doing it. In fact, helium is the only element in the universe that will not freeze into a solid at normal atmospheric pressure, no matter how cold it gets. To make solid helium, you not only have to cool it down to near absolute zero, but you also have to crush it under immense pressure. This makes it fundamentally different from every other element we know. When we compare helium to other gases, its uniqueness stands out. Hydrogen is lighter, yes, but its reactivity makes it dangerous for many applications. Neon is also an inert gas, famous for its use in bright signs. While most people only know helium for making balloons float and voices squeak, its true importance is hidden inside some of our most critical technologies. Its biggest and most important job is in the medical field, specifically inside magnetic resonance imaging machines. An MRI scanner uses a giant, incredibly powerful superconducting magnet to create detailed images of the organs and tissues inside the human body. For these magnets to work, their wires must be kept astonishingly cold to eliminate electrical resistance. The only thing on Earth that can do that job effectively is liquid helium, bathing the magnets in its negative 269 degrees Celsius chill. Without helium, MRI machines simply couldn't operate, and doctors would lose one of their most powerful tools for diagnosing diseases. Beyond the hospital, helium is a crucial partner in our journey to the stars. Rocket science is a delicate dance of volatile fuels and extreme pressures, and helium plays the role of the calm, stable supervisor. It is used to purge and clean rocket engines before launch, ensuring no stray ice crystals or contaminants are present. More importantly, it is used in a rocket's fuel tanks to push the liquid hydrogen and liquid oxygen into the engines. Because helium is so inert, it won't react with the explosive rocket fuel, making it the perfect, safe piston to power the launch. From the Saturn V rockets that took us to the moon to the modern rockets of SpaceX, helium has been the unsung hero of space exploration. In the mind-bending world of quantum computing, researchers are building machines that could solve problems impossible for today's computers. These quantum processors are incredibly delicate and must be shielded from any external noise or heat. Once again, liquid helium is the answer, creating the ultra-cold, stable environment these futuristic machines need to function. So, if helium is the second most abundant element in the universe, why on earth is it so rare here? The answer lies in a cosmic quirk of geology and physics. Most of the helium on our planet wasn't here when Earth first formed. Instead, it is created very, very slowly deep underground. This process starts with the natural radioactive decay of heavy elements, uranium, thorium in certain types of rock in the Earth's crust. Over millions and millions of years, the decaying elements release tiny particles called alpha particles. An alpha particle is simply the nucleus of a helium atom. It's helium in its infancy. The new helium gas becomes trapped in underground rock formations alongside natural gas. Over geologic time, it accumulates in subterranean pockets. That's why helium isn't mined like gold. It's extracted as a byproduct of natural gas drilling. Only certain natural gas fields contain enough helium, sometimes just a tiny fraction of a percent, to make extraction economically viable. Major reserves are concentrated in a handful of places: United States, Qatar, Algeria, Russia. That concentration makes supply vulnerable to regional disruptions. The real problem is helium doesn't like to stay put. Its atoms are extremely small and lightweight. Helium is a master escape artist. It seeps through microscopic pores in rock. Over millennia, it migrates upward through the crust. Once it reaches the atmosphere, its journey nears its end. Being much lighter than nitrogen, oxygen, it continues to rise to the edge of our atmosphere. There it escapes Earth's gravity into space, lost forever. That one-way trip makes helium non-renewable. Unlike oil, water, helium that escapes is gone for good. Every time we let a party balloon go, we are contributing a tiny, irreversible amount to this planetary loss. For decades, especially while the US held a massive strategic reserve, helium was treated as if it were cheap and abundant. That encouraged wasteful practices and artificially low prices, discouraging recycling and conservation. Now, with demand skyrocketing and reserves dwindling, we are facing the consequences of our short-sightedness. The growing helium shortage is no longer a distant theoretical problem. Its effects are being felt right now. The most immediate impact is on cost. As supply tightens, demand from the medical sector surges, demand from the tech sector surges, the price of helium has skyrocketed. Hospitals are seeing MRI operating costs rise dramatically. We are facing the consequences of our short-sightedness. This scarcity has triggered a global scramble to secure the remaining supply. Visual world map highlighting the few key countries with major helium reserves and the new exploration sites being prospected. Geopolitical tensions matter. A disruption at a production facility or instability in a supplier nation can send shockwaves. Nations and corporations are racing to find new sources. Geologists are re-examining old gas fields and exploring new territories. It's a modern-day gold rush, but for an invisible element. Thankfully, the crisis is also spurring innovation in conservation and technology. The most promising solution is recycling. In the past, helium used for cooling was often simply vented into the atmosphere. Today, sophisticated capture systems and reliquefaction systems are being developed and installed in hospitals and labs. These closed-loop systems can capture the evaporated helium gas, recool it back into a liquid, and reuse it, cutting down on waste by over 95%. While expensive to install, these recycling systems pay for themselves over time by drastically reducing the need to purchase new helium. It's a crucial step toward creating a more sustainable helium economy. Still, we are left looking toward a future where our most important gas is treated as the precious resource it is. Engineers are working to design next-generation MRI machines and scientific instruments that are more efficient and require less helium to operate. But these are long-term solutions. For now, we must grapple with the reality that every bit of helium matters. That little balloon floating away isn't just a lost toy. It's a lost piece of our ability to see inside the human body, to explore the universe, and to build the technologies of tomorrow. As we stand at this critical juncture, we have to ask ourselves a monumental question. As we use up this irreplaceable gift from the Earth's ancient past, how will our ingenuity, allow us to adapt? And can we ever find a way to create more?